Okay, so we have done some greedy problems, right? And I hope you are getting some clue on how to get started with grading. Right? So here, this is more about, okay, I have a problem and I have to find a choice that needs to be optimal. So I should start thinking about what kind of choices I can make. And then either I prove that they are not optimal by finding a counterexample, or I prove that they are optimal by the proof, directly the proof. So we have done two problems till now. One is coin change problem. Another is you can say interval scheduling, activity selection. Yeah, that is more appropriate. Activity selection problem. In both of these cases, we found the greedy approach and we proved those. Okay, and you saw that by using greedy algorithm, they were really efficient. You could do that. This was like order one time you can do, and this you can do in order and log in time, even if you have to sort. So, so yeah, this was quite fast. Now today we will again do some more greedy algorithms, and let's see how do we approach. So if you are feeling, oh, I don't know how to approach a problem, think as if you have to solve these problems and see how you will approach. Okay, so let me start with a problem. Now this is the problem that I'm giving right now is a variation of activity selection. Okay, so activity selection. It's not selection, it is activity scheduling. Okay, so the setting is different. Setting is very different. Let me explain what is the setting. So setting is that you have a single resource. Like we also had last time only one resource, one classroom. Okay, and set of n requests. Okay, just to repeat. Yes, till now everything same. But now what follows is different. So in the previous problem, what you had, each request comes with a start time and a finish time. I want to start at this time and finish at this time. Okay, I cannot start arbitrarily. But here, what we are saying, so each request comes with a time requirement, TI. That means how much time it will take to complete that request. Right? Time taken. Uh, so that means what is there, that for each request it is telling you, okay, I will need 3 hours. I will need 3 hours of the resource, right? 3 hours on the resource. And it has to be run contiguously. So I cannot say, oh, let me run you for 1 hour, then I'll take you out, and then again 2 hours. No. Continuously run for 3 hours. That's when this request will be completed. Okay, fine. Now each request comes with that. And your task is you have to schedule all requests. How will you do that?
So what do you mean by scheduling all requests, like taking all of the requests?
Yes, I want to schedule all requests this time.
Sir, we'll pick the request with shortest duration first.
Why?
So what is the optimality requirement?
Yeah, that is what I wanted to hear. So this is an ill-specified problem, right? Right now you do whatever you want, like who cares? There is no optimization problem here. So you can say, oh, fine, I'll schedule S1, like request one, request two, and so on. What is the big deal? They just need to run for the time. I'll run it for the time. Done. Right? So there's no optimization problem right now. So first of all, think what is the optimization problem, right? Before you even proceed. So now, good. So what is the optimization problem? Oh, so yeah, this is an ill-specified problem till now. Let me specify that for you. So each request has a time requirement. Okay, I want to schedule all requests, right? But there is no optimization here. So let me put something. So I say, okay, now you tell me. In this, okay, yeah, so you cannot tell right now. So let me give another thing. So let's say they come with a time requirement, Ti, and a deadline, Di. So each request comes with a time, that requirement, and a deadline, Di. Okay. Now, do you think you can schedule all requests, satisfying all the deadlines? Is that possible?
Not always.
Not always, right? Like suppose I have a request. I have a request that comes at time 1, or no, does not come at time. It only gives me time. So suppose I have a request as that has T1 as 10 and deadline is 10. Second request that will take say 5 and deadline will be 5, let's say. And my task is to schedule all the requests. So can I do that by satisfying the deadlines?
Sir, is the deadline a specific time or
Time.
period
It's
of
time.
time?
It's a time. Period of time does not make sense, right? Because we are already given the period of time. This needs 10 amount of time. This needs 5 amount of time. And deadline is absolute time. After, say, after the time, then the resource became available. You need to complete by 10, or you need to complete this by 5. So can I schedule all that satisfying the deadlines?
No,
No,
sir.
sir.
What are the possibilities? I do job 1, then job 2. In this case, I will satisfy for job 1. For job 2, I will finish at 15. So I cannot satisfy that deadline. If I do the other thing, job 2, job 1, for job 2, I will satisfy, but job 1, I will not satisfy. Okay, so that means even now it is not possible to schedule all the requests. So even now the problem is not fully specified. At this time, you could have asked, oh, what is the optimal subset now? But now, let me,
Excuse me, sir.
yes.
So can you please explain about what is deadline?
Deadline is the time by which you want your task to be completed, roughly. Okay, so
Sir,
yes,
sir, I didn't understand the problem statement. Sir, can you please explain it once?
okay. Did you understand the example?
No, sir.
So there's a single resource. Let me give more concrete example. Let's say I don't know if you do code. I mean, I know you can do code, C code, but code on some servers. So suppose you have a server on which only a single person can run the code. Okay, on which a single code can be run. Generally, like here we have GPU servers where you do use your deep learning codes. But of course, there are multiple can run, but let's say only one code can be run at a time. Now, there are many students, or they want to use the resource. So they say, okay, I have a code that will take 10 minutes. Okay, I need it to be completed by 10 minutes after the resource is available. Let's say resource is available at 12. I need it to be completed by 12:10. Okay. Second person says, oh, my code needs 5 minutes to run. I want it to be completed by 12:05. 5 minutes after this is available. Okay. So like that, each one is telling what is the time their code will take and why, when they want it to be completed. Now what I'm saying, and suppose you are a person, you say, no, I want to satisfy everyone. So I want to schedule all the, I want to run all the codes. So immediately you can see I cannot satisfy all the deadlines. Can you see that?
Yes, sir.
Right? So I cannot satisfy all the deadlines. So, okay, so I cannot solve this problem. No. So I need to change my problem slightly. So I say, okay, each one gives me a deadline, but I can say, okay, they have a deadline, but let's say, suppose I am allowed to run some requests late. So, okay, you told me I want it completed by 12:05. No, I will take some more time. So I cannot solve the problem. I mean, I cannot do it by deadline, but I will take some more time. So let's say that is allowed. Suppose I am allowed to run some request late. Then again, this is an easy problem. Then you can run everything, right? Some will be late, some will be on time. So that is where again I have to specify that further. But you want to optimize something. So what you want to optimize? But you want to minimize the maximum possible lateness for any request. What is this lateness? Okay, what is this lateness? So here I will again write it formally. So suppose there are n requests. So n requests, and they have a time t1 to tn, and they have a deadline d1 to dn. Okay. So for a request I, so you will schedule them on the resource. So request I will start at some time, say s of I, and at f of I, and where f of I is nothing but s of I plus ti, right? Fine. At some time it will start, and sometime it will end. Si, fi, and this time is ti. Now there are two possibilities. Possibility one, so case one, so where the deadline di was larger than fi. So in that case I say, okay, this is on time, the request is on time, no lateness here. But case two can be that the deadline was earlier. Case two, di was less than fi. In that case, this is late. I ran it late. So what is the lateness? I simply define how much was the request late. Fi minus di. Lateness Li is Fi minus di. Okay, is the definition clear for lateness? In this case, lateness is 0. In this case, lateness is Fi minus di. Okay. Now, I want to minimize the value of okay. So now, okay, let me write it. What is the maximum lateness? Which request was late by the maximum time, right? How will you define that? Max of I, Li. That is the maximum lateness. Now you want to optimize is that, okay, maybe some people will run late, but I don't want to discover someone like really bad. So I said, okay, the maximum amount of this lateness I want to minimize. I don't want to run someone like really late. So I want to minimize the max value of lateness. That means, okay, whatever maximum lateness I will get, that should be minimum. Okay. Okay, now tell me if you did not understand. Yes.
Sir, lateness means each object late some amount of time, so we have to sum all its.
No summation. There is no summation. I defined lateness per activity, Li, is Fi minus Di. Did you understand that?
Yes, sir.
Right. Now you see, you have say, 50 students trying for a resource. Say student 1 uh, gets late, his request is run late by say 2 minutes. That is the lateness. For student 2, it is run by late by 3 minutes late. For student 5, run by 10 minutes late. Some student on
Yes, sir.
time, on time. So like that, right? So now you
Sir,
can find the maximum value.
means maximum of all the students, maximum
Maximum
lateness of all
lateness.
the students.
Yes.
Okay.
Of all activities.
And we have to minimize this maximum value,
Yes.
sir. Okay.
Yes. And
Okay.
you don't want this value to be very large. I say, okay, it's okay if I make everyone late by same amount, say, rather than making a single person late by 100 minutes. It's okay if I late everyone by 10 minutes, but it's not okay if I do everything on time, but one person is late by 100 minutes. Okay. So you want to be
Okay.
fair. So you want to be fair to everyone.
Yes,
That is,
sir.
so you want to minimize this value. Okay, is the problem clear? Now what is the problem that I'm trying to solve? I want to minimize the maximum lateness. Okay, so immediately you think, like looks difficult, minimum of max. Oh, how will I solve this? So let me take an example. So suppose I have 3 requests. Job 1, this TI is T1 is 3 and D1 is 6. Job 2, so it will take 2 minutes. T1 is 2 and D1, oh sorry, D2 is 4 and job 3, T1 is 1 and D1 is 2. D3 is 1, D3 is 2. Okay, so how can I schedule that so that the maximum lateness is minimized? So I can do like this. I can do job 1, job 2, job 3. If I do in that manner, what will happen? So job 1 is scheduled first, finishes at time 3. Then job 2 finishes at time 5. And job 3 finishes at time 6. What is the lateness for job 1?
0.
0. Yes. What is the lateness for job 2?
1.
1. What is the lateness for job 3?
4.
4. So what is the maximum lateness?
4.
Okay. So, okay, here I got 4. But somebody can say, okay, why don't I do job 3, job 2, job 1? So if I do job 3, job 2, job 1, finish time 1, 3, and 6. And this has lateness 0, this has lateness 0, this has lateness 0. So here the maximum lateness is 0. So I prefer this solution. I'll not prefer this solution. Okay? Just wanted to understand if the question is clear.
So in job one, okay, sir, okay.
So can we be provided with a job which has time duration greater than deadline? Like we won't be provided with such cases.
Yeah, let's assume like nobody will say, oh, I will run a code for 10
Yes, sir.
minutes and deadline is 5. How is that possible? So yeah, they should be same. Yeah, sure. You can assume that. Okay. Good. So now, see, now you got this problem. Now, how should you approach this problem? So I say, okay, what is all that is available to me? Now, I will not talk about dynamic at all today, okay? So just think in terms of greedy. So what I have n requests. Each one has a time and a deadline. That's all I have. That's all I have. So I need to do something with these. I need to do something with these times and deadlines, right? So what are the greedy choices that you have in mind? You can write down all the possibilities. So what are the possible greedy choices?
Choose the one with earliest deadline.
Approach 1. Choose the job with the earliest deadline. Oh, this is deadline is earlier. Let me finish this first. Oh, finish the job that needs to be finished first. Makes sense. Any other possibility you can think of?
Sir, choose
Sir,
jobs
choose the
according to
job
the value of
which has
DI minus
similar time
TI.
duration.
Choose the job with the minimum value of DI minus TI. Yes. So that means, oh, it is giving you very little time. So TI and DI are very, very close. So yeah, I can call it slack time. It is giving very small slack time. It needs 10 minutes, deadline is 11. Oh, very little time it is giving. So let me finish a job that has the minimum DI minus TI. Good. What else?
TI is the starting time, no, sir?
No, TI is the time duration. There is no starting time. You have to schedule it. You can schedule at any point of time. The start time,
Okay, sir.
finish time are not given. Only the time duration is given. Okay, anyone else? Give me a third approach.
Lowest TI.
Yeah, why not? Choose the job that will take little time. Let me just get this job done. Choose the job with the smallest duration. So minimum TI. Okay. Anyone can think of any other approach, or we are okay with these three? Okay. So three approaches. Good. See, that's how you should start. You say, okay, these are the three things that are coming to my mind. Let me write down. Anybody can think of anything else, we will write down that also. And then let's see how will we proceed further. Okay, fine. Now, what is the rule of greedy? For each approach, I think in tutorial also, Kaushik told you, try hard to prove that this is not optimal, right? Try hard to find a counterexample. If you can find a counterexample, that means not optimal. So don't even worry about this. If you can't find a counterexample, then you can think, oh, can I prove this? If you can't find a counterexample, then think, can you prove it? Okay. Or if you can't find, then prove. Optimal. Okay. Now, last time I went from 1 to 3. This time I will go from 3 to 1. Okay. So I'll go to 3 to 1. Let's see approach 3. Approach 3. Job with the shortest duration. Then anyone think of a counterexample.
Job with smallest duration but last deadline.
So what you're saying, see, you have to think of a counterexample that also requires thinking. So what is the greedy choice? Greedy choice is that if I choose a job with the shortest duration first, I'll get an optimal solution. So then you have to think like an adversary. Oh, how will I make an example such that this greedy choice will not be correct? So then you have to think like an adversary. So I have to think an example where I have a job 1 and job 2. Let's take a simple thing. Don't think about, oh, I'll make a very large counterexample. No. Always think of a very small counterexample. Otherwise, it becomes difficult. So let's say I'll take 2 jobs. At least 2 jobs are needed for a counterexample. Now, what will happen? Job 1 will have very small duration, but it can have very large deadline. Say T1 is 1 and D1 is 100. Very large deadline. You can take as much time as you want to finish. And job 2 takes more time, right? But its deadline is very, very strict. So D2 is 10. So that means now what you have done with this counterexample, you have ensured that the greedy choice will select the shortest duration job first, but that had a very large deadline, right? But optimal solution will be different. So what is the greedy solution? Job 1 has the shortest duration, and then job 2. Greedy solution. What is the lateness? Lateness of job 1 is 0. Lateness of job 2 is what?
1.
1.
It finishes at time 11, deadline is 10. So lateness is 1. And what is the optimal solution? I will do job 2, then job 1, lateness is 0, lateness is 0. I am happy. Okay. Okay, so this is the process. Good, very good. Now let's take approach 2. Choose the job with the minimum value of di minus ti. Now, sometime you might want to think, oh, maybe my previous counter example may still work as a counter example. So what happens with this example here? For this example, this approach will give you optimal solution or non-optimal solution?
Optimal solution.
Optimal solution. So I need to do some more work. Previous problem, I will choose job 2. Job 2 had D2 minus T2 was 0. And for job 1, D1 minus T1 was 99. So I would choose job 2, job 1. That is giving me optimal solution. So there's a possibility this approach is correct, right? But that does not mean it is correct. So can you think of a counter example?
Yes, sir. If we take T1 as 6 and D1 as 10 and
Mhm.
T2 as 4 and D2 as 9, so it is not giving the optimal solution.
Okay. So what you are saying, counter example. So job 1, so T1 is 6
6.
and D1 is 10. And for job 2, T1 is
4.
5,
4.
4. And D1 is
9.
9. So what is the select time? So here select time is 4, here select time is 5. Yes, di minus ti. So as per my greedy choice, I schedule job 1, then I schedule job 2. Okay, so job 1 finishes time 6 and job 2 finishes time 10. So what is the lateness? L1 is 0, L2 is 1. Okay, what is the optimal choice? So there's only one more choice. Let's see what happens in the other choice. Job 2 and job 1 if I do job 2, I finish at time 4, then job 1 finish at time 10. So what is the lateness? Zero.
0 and 0.
Okay. So yeah, so then this is not a good counterexample then. Then both greedy and optimal are giving me the same value. So same.
So greedy has one, right? Lateness.
Huh? Sorry?
Greedy has one lateness.
Greedy has
Sir.
one lateness.
Greedy will give 1.
Yes, sir.
Oh, sorry. I'm sorry. I'm sorry. Here, job 2 had a deadline of 9, but finishing at 10. Yeah. So this had lateness of 0, this had lateness 1. So yes, you have a counterexample. I'm sorry. You give it correct counterexample. Okay, so we have got a counterexample for approach 2. So yeah, in general, if you cannot think of it, think like that. Oh, what about a job that I have to finish very, very early but gives me some more slack time. So something like, I'm just giving you a simpler counter example, but yeah, this is a good counter example. Something I have to finish very early, and I have some slack time. Another job that takes more time, say 100, and its slack time is, there is no slack time at all. So what will you do in that case? You will first schedule, as per your greedy choice, you will schedule job 2, then job 1, right? But then your lateness will become 99. You will get a lateness of 99 in your greedy choice. But in optimal solution, what you will do, you will first schedule job 1, then job 2. So your lateness will become 1.
So from greedy, we choose first. We will get lateness equal to 1, right? Even
No,
then.
greedy solution is D2 minus T2. Minimum D2 minus T2. Minimum DI minus TI. Here DI minus TI is 0. Here DI minus TI is 1. So you will choose this first and then this, as per your greedy solution.
No, sir, I'm saying lateness is 1.
No, why? Because you will first schedule job 2, then you will schedule job 1. For job 2, lateness is 0, but this job finishes at time 101. Its
Okay,
deadline
sir.
was 2, so lateness is 99. Okay, but your optimal solution lateness would be job 1 and then job 2. Time 1, time 101, so lateness is 1. Okay. See, both are correct. I'm just saying if you want to think, you can also think of a simpler counter example. But this is a perfectly valid counter example. So, okay, so approach 3, approach 2 are done. So all bets on approach 1 now. So hopefully nobody can find a counter example. Let's see, anybody can find a counter example. Choose the job with the earliest deadline. Approach 3. Choose job with the earliest deadline. One thing you can quickly do, if you can think any of these examples are already a counter example for that. So here, did you choose the job with the earliest deadline? In this case, any optimal solution?
Yes, sir.
Yes, this works. Did you choose a job with the earliest deadline in the optimal? Yes,
Yes.
I chose job 2. Did I choose the job with the earliest deadline in the optimal? Yes, I did. So for all 3 cases, this works. Okay, can someone think of a counter example? So these counter examples will not work.
In the previous example, D2 has 102.
Okay, let's do it. So job 1, T1 is 1, D1 is 2, and then T2 is 100, D2 is 102. Is that what you're saying? Somebody?
No, sir, no, sir.
No, so this will not be a counter example. Yeah.
Will it have a counter example?
Yeah, that's the question. So that means we can't find a counter example right now very easily. So then maybe this approach is correct. Maybe this approach is correct. So here I can say, okay, maybe this approach is correct.
So, but how we can be 100% sure? So
I said that you cannot be 100% sure unless you prove it.
yes, sir.
Okay, so that's why I put in maybe this is correct, but then that means I have to prove it now, prove that this is optimal. So right now why you are little bit sure, because you could think of 3 approaches and you could find counter example for 2, and for all the examples this approach 1 was giving correct thing. and you could only think of 3 approaches. So that's why you have a feeling that maybe approach 1 is correct. Okay, and it looks okay. I will take the job with the earliest deadline first, right? Makes sense. But yeah, that is not sufficient. I have to prove it. So let's prove it. Let's prove it. So what will be the algorithm for this? Okay, sort the jobs as per the deadlines. So now what will happen? D1 less than equal to D2, Dn. Okay, now schedule in this order. Okay, schedule in this order. So suppose this was available at time S. So then first job will run at S plus T1, and this will run for another T2 time, and so on. So when all the jobs will be over, S plus summation Pi. That is when the jobs will be finished. That is the finish time, overall finish time. Very easy algorithm. So,
Sir,
yeah.
while sorting the jobs as per deadlines, means in case of ties, how should we break, or any arbitrarily we can
Doesn't
break
matter.
ties?
It won't matter here. Anything you can say. You can say the one that comes earlier index, whatever. Does not matter.
Means shouldn't we take that one who takes longer time? Should
No, does not
it is not like that. Okay.
not matter.
So, but in a example, I think that it matters. Like I saw an example, it should be that we should choose the largest time duration job if there is a tie.
No. No. We can prove it. Let's say you have only 2 jobs. Okay. They have the same deadline. D1 and T1 and T2. And what you're saying, T1 is larger than T2. I'll prove for general, not write some numbers. I'll prove for general. T1 is larger than T2, right? So there are 2 ways you can schedule these. I'll put job 1, then I'll put job 2.
So the lateness will be T1 plus T2 minus the common deadline.
Good. So
Okay,
maximum
sir,
value will be
understood.
T1 plus T2 minus D1.
So it
What
doesn't
you
matter
use-
whether T1 comes or T2 comes.
Good. So it doesn't matter. Right. No, but yeah, it's very important that you are asking the doubt, because you can see that, yeah, we can prove it. It's not at all why we did not do anything, because it does not matter. Okay, very good. So yeah, that means if 2 jobs have the same deadline, I can schedule in any order. That way I will not worry about equal deadline. Okay, that is important. Otherwise, yeah, in sorting, this is a problem. So now I have to prove it. Okay, so how will I prove it? Proving is very standard in theory. Okay, but let's do. Let's do. So what is my greedy choice? My greedy choice is, okay, schedule jobs in increasing order of deadline. And for timing, forget if the 2 might have same deadline. Assume that all of them have distinct deadlines. Will not matter, but for the ease of argument right now. Otherwise, you have to take care of equal signs. That does not matter, but yeah. Still, you have jobs in increasing order of deadlines. And so that means for job I and job J, if Di is less than Dj, that means I is scheduled before J. So that's all my greedy choice. Now you want to prove optimality. So to prove optimality, what you have to do? Assume there is an optimal solution. Assume there is an optimal solution. Oh, okay. Now I need to see, okay, how O can be different from G. So this is your G and this is your O. See, what is the idea? You have to see if O is different from G, can you make some changes to O so that it starts getting closer to G? Okay. So if O is not equal to G, change O such that optimality is maintained. It remains optimal and it starts getting closer to G. And it starts getting similar to G. That is right. Okay. So here we will talk about one argument that we did not say earlier. Okay. So now, see in greedy solution, what will happen? So you have job 1, 2, 3, 4, n, and such that for any ij, di is less than dj. Right? That is a greedy schedule. Now take any arbitrary schedule. If it is different from G, what should happen? If it is different from G, what can you say?
Sir, at least 2 of the places in greedy schedule would have been swapped.
Right? So there will be at least some ij such that I is scheduled before j, but deadline of I is larger than deadline of j. It would have to happen for any other schedule that is not greedy. At least at one place this will happen. Do you agree or not agree? I'm just putting that in this audit order here in greedy. So if anything has to be different from this, that means at least one swap has to happen, right? I should do before j and deadline of I is last than deadline. So we call this as an inversion. An inversion. You can call it a swap, whatever. You call it a swap if you found it easier. I'm calling it inversion, that di is larger than dj, but di is scheduled, I is scheduled before j. Okay. Now I can say now my optimal solution, there are two possibilities. Case 1 has no inversions. That means it is same as G. And case 2 has at least one inversion. At least one swap. Whenever you do not agree with me, just interrupt me. Otherwise, I'm assuming you are following this. Okay. Fine. And now what is your task? Very simple task. This optimal solution will, in case 2, will have an optimal solution. Now you now you swap I and j, and you show that this will have a better solution. This will get a better, or it will remain, its optimality will not change. So, or remove the inversion. So in this case, remove the inversion and show that it is still optimal. It is still optimal. Or better than optimal. How exactly I will do that? Okay, so there's a trick. The trick here is, you see what you are seeing? There are some job. Okay. I'll just put some names A and B. So DA is larger than DB and A is scheduled before B in optimal solution. Okay, A and B can be any far apart, right? A can be at some place and B can be at some place. Now, if I try to just see what would have happened, so A has a larger deadline than B, right? So if I go from A to B, anything can happen, deadline may increase, then they will decrease, right? Or they may increase, whatever. Anything can happen. But DA is larger than DB. Something can happen, anything can happen. But what I'm sure, at least there will be one point where the deadline will decrease immediately. So there will be two consecutive jobs, I and J, such that the deadline decreases for the first time. If DA is larger than DB, it has to happen at two consecutive. Maybe A and B are consecutive, then it is happening. But otherwise, what may happen? It may increase, it may decrease at B, or it may decrease, increase, whatever. But you can always find two consecutive jobs where deadline decreases for the first time. This can be directly DA to DB or something in between. Do you agree? Some point it will decrease for the first time. And let's call those jobs I and J. So job I and job J. And DI is larger than DJ, and DI and job I is scheduled just before J. So job I is scheduled just before J in my optimal solution. Are you following this reasoning? See, this is helping me. This now my proof will be very simple. If I would have done for arbitrary ING, I had to take care of so many things. But now I'm talking about two consecutive jobs that I'm swapping, that I'll swap. And that will make my proof very, very easy. What I will have to show, if I invert this, then my solution remains optimal. Okay, that's all. In optimal solution, I have some things scheduled. So you have to make your life simple.
Sir?
Don't complicate. Yes, tell me.
Sir, can you please explain this logic once?
Did you understand the logic that optimal solution, if it is different from greedy, has to have at least one inversion?
Yes, sir.
Right. So let's say we talked about inversion. Yes, let's say some arbitrary position, some A and B. A is scheduled before B, but DA is larger than DB. By definition of inversion.
Yes, sir.
Right. So I'm saying, think widely. What all can happen? It may go down. It may go up. Anything can happen. Go down and up or whatever. Right. So whatever you can think of, because DA is larger than DB, there will be two consecutive pair of jobs such that I and J such that it decreases for the first time. Do you agree with that or you don't agree with that? Let me just make DA slightly above so that you can also visualize this. DA is higher, DB is lower, right? If you go from DA to DB by any path, you can go up, down, whatever. At least once you will have to go down. Do you agree?
Sir, so you mean to say that there exist two, I mean I and J, where DI is greater than DJ?
Yes, and they are consecutively scheduled in the optimal solution. Consecutive jobs.
Sir, but we have assumed that there is only one inversion, DA-DB.
No, we have said at least one inversion. We have said at least one inversion, and this is what you are finding, A and B. Let's say there is at least one inversion. So see, if there's only one inversion, then this A and B will be I and J, right?
Yes, sir.
So now this is for general case. Even if there are multiple inversions, I don't care. So then also I will have two consecutive jobs, I and J, such that deadline decreases for the first time.
Yes, sir. I understood.
Okay, got it. So I'm saying I did it to make our job life simpler because we have to prove, right? So now what will happen in optimal solution? I'm scheduling things up to here, things before job I. Now I schedule job I, and then I schedule job J. Okay, and then I continue scheduling other things. Okay, now I'm saying you swap ing. That means you remove an inversion. So then what will happen? Job J, then job I. And if you swap ing, nothing changes. So whatever was there in the left remains same. Whatever was there in the right remains same. No change at all. Only changes the swap ing. Okay, this is all you do. Now what we have to show that by doing the swap, my solution still remains optimal. Okay, or better than optimal, whatever. So I get an even better solution or same. It is not worse than optimal solution. This solution cannot be worse than O. If I can show that, that means whenever I get an inversion, you swap it, it will not be worse than O. That's all. And then I'll get a greedy solution with no inversions. That is the idea. Okay. So now I have to now focus on this. I have to prove that if there is a single inversion that I'm swapping one inversion, I will not get a solution worse than O. How will I prove it? Okay. So let's formally define this. So, so let's say I define, suppose each request R is scheduled at some time SR and finish at time FR, right? And FR is SR plus TR. I'm not using I because ing we are using here. Okay. Now I define the solution, the optimal solution for O, LH maximum of LR. Among all requests, what is the maximum LR? LR we have defined. What is LR? Depends on deadline. So what is the deadline? DR. Okay, and they had a time TR. So that is my solution for optimal solution. Okay, this is for schedule O. Now this is your schedule O. Suppose this is your schedule O prime. So in O prime, suppose what will happen now? So what is L? L is max of L1, L2, Li, Lj up to Ln. This is the max of this. Okay. In O prime, suppose I denote things by R prime or say by a bar. Okay. So in O prime, I use bar to denote things. So L bar is max of L1 bar, L2 bar, Li bar, Lj bar. Okay, so they start at some SR in O. This is in O. In O prime, this will be some R bar. SR bar. So FR bars. DR and TR remains the same. Is that okay? Ln and bar. This corresponds to O. This corresponds to open. Now, what can I say about all these things?
Sir, they are same
Sir,
as
Li bar.
Except from Li bar and Lj bar, others are same.
Everything is same, right? So here, what I can say, this block is same as this block, and this block is same as this block. They are identical. So only difference is here. Okay. So if the maximum value occurs in this block or this block, it will not change, because these blocks are not changing. So if the max here is in this block or this block, the solution is not going to change. The only way solution can change if the max happens either here or here. Okay, so that means if L is max of Li Lj, and then L bar can be different. If L is this, then L bar can be different than L. Otherwise, L bar will be same as L. Okay. So now we should concentrate only on this. What happens to Li prime Lj bar? Okay. So here, this was finishing at time Fj. So what was Lj? What was Lj? How do I define Lj?
Dj minus Fj.
No. Fj minus Dj. Right? How far I
Okay. Yes,
from
sir.
the deadline. Okay.
Yes, sir.
And Li is Fi minus Di. Assuming it is larger than 0. Just. Now this, what time this is finishing? Can I say this is also finishing at time Fj, same as this?
yes, sir.
Yes, sir.
Right? Starting at the same time, finishing at the same time. Okay. Now, so now let's now focus on only. I'm sorry, I'm going very, very slow just to ensure that you understand this. I will take some more time. I'm sorry. I hope you won't curse me for that. But yeah. Lj bar, Li bars. Okay. Now, job J I'm scheduling before, and job I I'm scheduling later here. What can I say about okay. Good. See, even from Li and Lj, can you always say that which one will be larger?
LJ.
How can you say
LJ.
Lj is larger than Li? Why?
Sir, Di is greater than DJ.
And Fj is greater than Fi.
Yes, very good. So here you see Fj is larger than Fi and Dj is smaller than Di. Yes? Dj was smaller than Di. So that means if you take a minus, that means so Fj plus minus Dj. So it's not easy to see that both of these quantities are larger than these quantities. So that means Lj is larger than Y. Anybody who cannot see that, let me know. Lj is larger than Li. Here. Okay, so that means so my task is even simpler. So I need to now focus only on Lj. Okay, so now only thing I have to prove is that if Lj prime and Li prime, if this is less than Lj, even equal to will work, or and this is also less than equal to Lj, that means O prime, the solution for O prime or O prime is not worse than O. Let me just write that. O prime is not worse than O. Do you agree? That's all I need to prove. The maximum lateness
Yes,
is not
sir.
increasing, right? So that's all. Let's do that. So, okay. So now let's write things. What is Li prime? What can you say about Lj prime? First of all, Lj prime. Can you very quickly say Lj prime is less than Lj?
Yes, sir.
This is
It would be Fj minus Di.
Fj bar, because the time has changed. I'll just write it Fj bar. I'm sorry, because job J is finishing earlier. I'm using bar. So this is same as Fi bar. Okay. So in the new thing, everything is with bar.
Okay, sir.
Okay. But this is also same as Fj. So Lj bar is Fj bar minus Dj, and Fj bar is less than Fj. So that is less than Fj minus Dj. So that is equal to Lj. So that means Lj bar is less than Lj. Proven. Yes.
Yes, sir.
Okay. Now Li bar. What is Li bar? That will be Fj, right? Finishes at the same time. Fj, Fi bar is same as Fj minus Di. And because Di is larger than Dj, so this has to be smaller than Fj minus Dj. Because Di is larger than Dj.
Sir?
Yes.
Sir,
Yes,
Lj
yes.
bar is Fj bar minus Di.
No. Oh, this you are saying. Lj bar is Fj bar minus Dj.
Di.
DJ.
Sir,
Why
job
DJ?
I is means in bar place, job I is there, sir.
No. Bar is just the new schedule. Bar is just the new schedule. So see, I'm scheduling job J before job I. For a given job, deadline does not change, right, on the schedules.
Yes,
So
sir.
job
So Di should be Di, no, sir. You have taken Dj.
see, LJ
Is
bar
the
will
right
come.
one.
Okay. Just let me tell you. LJ bar is the lateness for job J in the new schedule.
Okay.
So that
Okay,
is
sir.
LJ bar time when it finishes minus its deadline DJ.
Okay,
And
sir.
FC bar is less than
Got
FJ.
it, sir.
Okay. So this is less than FJ. Similarly, Li bar is Fj minus Di. This is actually Fi bar minus Di, but Fi bar is same as Fj. So I could have put one more step, Fi bar minus Di, which is same as Fj minus Di, which is less than Fj minus Dj. Do you agree with that? So that is equal to Lj. So that means Li bar is less than equal to Lj is also proven. So once I've proven both of these, that means yes, maximum lateness cannot increase. So this O prime is not worse than O.
Sorry, I
I'll
have a doubt.
pause for a minute for any doubts.
See here, L1, L2 are the latenesses for each of the job, right?
Yes.
So shouldn't we sum them up? Why are we taking maximum?
No, this is our problem. This is our optimization problem. Optimization problem is that I want to minimize the maximum possible lateness by any of the job. So each Li tells me what is the amount of lateness for the job I. I want to minimize that. So I want to minimize the max of all these.
Okay, sir.
Okay. Now,
Sir,
yes.
sir, but here in the very right hand side, you have proved Li bar is less than Lj.
Yes.
Sir, but we need to prove Li bar is less than Li, right?
No, no. That's what I said. Your maximum lateness should not increase. Earlier we said if the maximum lateness is lying here or here, you don't care, it will not change. So it has to be either this or this, then all it can change. Now,
Yes, sir.
among these, we already proved that Lj is larger than Li.
Yes, sir.
So maximum lateness can be either Lj or it will be somewhere here.
Yes, sir.
So then I have to only care about Lj. So if I can prove that the lateness I get, Li prime and Lj bar, whatever, if both of these are less than Lj, I'm done.
Okay. Yes, sir. Yes, sir.
So that is what I'm proving. Lj bar is also less than equal to Lj. Li bar is also less than equal to Lj. I'm done. That means O
Okay.
prime is not worse than O. That's all. Okay. And this gives you a very interesting argument, the inversion argument for
So
proving.
can you clarify with this FJ bar what it is?
Oh yes, I'll explain whatever doubts. That's why I'm going very slow. Yes. Tell me exactly your doubt and I will explain.
Yes, sir. FJ bar is the time period required to complete job I
No.
or job J?
No. So that's why you are making mistakes. So you see, each job comes with only two things, TR and DR. Only two things are fixed. How much time the job will take, TR, and what will be the deadline for the job, DR. Everything else depends on your schedule. That is where in everything else I'm putting a bar. But TR and DR are fixed. They will not change. So what is FR? FR is telling me in schedule O, what is the time when job R will be finished, FR. But in schedule O prime, it will finish at FR bar. That may be different than FR. It's the finish time in that schedule. No, does not come with the request. You define when you are starting the job. If you are starting at SR, SR plus TR gives you the finish time. Does that clarify your question?
Yes, sir.
Okay. That is why you see when I changed I and J here, I said, oh, this time is FJ bar and this is FI bar, which you can see is same as FJ, which you can see that this is same as FJ because I'm not changing any schedule. I'm just swapping. Any other doubt on this?
So by interchanging ing, there may be a chance that maximum of L bar can be shifted to right or left.
You see what we have done. The schedule here is exactly same as to here, up to here. The schedule here is exactly same as here. Now you tell me how can any of this be different, their lateness?
So I'm not saying that these both are different.
Okay.
By changing ing, like in orders, we are only changing ing position, no sir.
Yes.
But there is a chance of shifting of the maximum of O dash.
Oh, very good. What you're saying, it may happen, but earlier the maximum was here. Now maximum remains here.
Yes, sir. Yes, sir. Yes, sir. That's what I meant.
You only care about the value of that. That's what I'm saying. So if it was here, it cannot change. The only thing that can change if it was here. It can either go, it can only go less than this. Now if it was here, that means this value is larger than all these values already. Yes. So if it got shifted to this will remain, I mean, this value will be smaller than this value. So why do you care? Are you getting this reasoning? Very,
Okay, got it.
right? If it is here, this is anyway smaller than this, so I don't care. So what I'm showing, this value will remain less than. If these two things are less than this maximum lateness here, That's all. Even if it shifts here, doesn't matter. That will not shift. Yeah, it can shift here also. Why not? That it may happen that the second largest was here. So the largest now can shift here. But still, that will be smaller than this value. That is the reasoning. So only thing I have to prove that Li bar and Lj bar are less than this Lj. That's all I have to prove. And I'm done. Okay. Any other question? See, I'm here. We will not do this proof again, possibly. So if there are any doubts, anything that you could not follow, why I'm doing this. See, why I'm telling this is a very critical, a very important way of proving greedy techniques. Because what you do in greedy techniques, you do some ordering, right? And in a greedy solution, things will be in a particular order. And this inversion argument can be a very generic argument you can use for many different greedy to prove optimality for greedy algorithms. You can use an inversion argument. Okay, I have no inversion based on a certain property. In my optimal solution, there will be at least one inversion. Can I show that if I remove that inversion, removing the inversion, I go from O to O prime, and O prime is not worse than O. That means yes, whenever I get an inversion, I can remove it. I can get a solution not worse than O. That means from O, I can use a sequence of steps to remove inversions to get to G. I can obtain G from O by removing inversions. And G is, that means G is one of the optimal solutions. Here also you're saying that, suppose you had an inversion, now you remove that inversion, there's one less inversion, and you did not compromise optimality. So there will only be a finite number of inversions, right? You can keep on removing one by one by this technique, and you will obtain a greedy solution finally.
So sir, here for O we just made an inversion and again we change it to O prime by making F with the final times Fj bar and Fi bar, and we proceeded to prove not worse.
So this is just for proof, right? This is just a proof argument. In general, you are just now proving that yes, by this method I can remove inversions, I can obtain a solution that has one less inversion. Keep on doing that, you will obtain a greedy solution. Okay, that has no inversion, no inversions. Okay, and that is an optimal solution then, because you are not compromising optimality while you are removing an inversion. So this is a general technique you can use for proving various greedy algorithms. Okay, and we have already seen if there are multiple requests with the same deadline, it does not matter. I can schedule in any order. Okay, that will not change the basis. So that's all. That's all you need for the proof. And what is the complexity? Runtime complexity for this algorithm?
Sorting complexity.
Sorting. This is order and log n. Okay, at some point of time, we will tell you how to do it better than this. Right now, you just say that we can do it in order and log n time. We have to just sort. Okay. After your DP, I'll tell you how to do it even better than order and log n. Right now, if you do it order and log n, that is good enough. Okay, good. Okay, it's already 11:20. I wanted to give one more greedy algorithm, but I'll do what you say. If you want, I can do it. Otherwise, I'll just leave that. If you think I can do one more greedy now, within next 30 minutes, I'll do. Otherwise, I'll leave. I don't hear anything. Okay.
Sir, can you repeat your last statement, sir?
I said I wanted to give one more example for greedy. You want me to do that, or you think these are sufficient examples?
Sir, please give it.
Okay, sure. That's all I wanted to ask. Yeah, this one will be simpler. This one will be simpler. You can relate to something that you have done earlier. Okay, so I'll do it faster then. We'll do it slightly faster. So okay, so I have a problem. So what is the problem? So this is called a knapsack problem. Very famous name, knapsack. Okay. Uh, what is a knapsack? So I am a thief. I am a thief. I go into a store. In the store, there are various items. So suppose there are 3 items. So item 1, so each one item has a weight, right? So this is 10 kg, and it has a price that I know. It's written down, the item. This is $500. Then item 2, 12 kg, and this is $540. And item 3 is 3 kg, that is $90. 3 items. Now, knapsack means I have a knapsack. So thief has a knapsack.
Excuse me, sir.
Yes.
What is the weight of the third one?
Okay, it's not really big. 3 kg. 3 kg. Okay. So knapsack, I don't care how I can fill as much as possible up to the capacity. So knapsack has a capacity W. So let's say suppose 15 kg. Okay, 15 kg. So and I'm a thief. I want to optimize my value. I want to take as much value of goods as I want, as possible. Optimization problem. Take as much value as possible, subject to the capacity of knapsack. So what will you do? Tell me. If you are a thief.
Determine that per kg value and then pick the one with the highest value first, greedily.
So yeah, very good. But yeah, that's why I want to say this problem is still ill specified. Why this problem is ill specified? Because
Sir,
yes.
take any number of these 3, like I can take any number of these 3 objects, like 3 kg 5 times or 12 kg
No,
2
yeah, that
times.
is what this problem is not fully specified. What I'm saying is that, so now I need to specify a few more things. First of all, this is all the quantity that I have in the store. Okay, I have only 10 kg of this, 12 kg of this, 3 kg of this. Now there are 2 variations that are possible for this problem. In case 1, these can be like a single item, right? They are single items. So say 10 kg of 10 kg of a printer that is 10 kg of it, a laptop that is 12 kg, whatever, a machine that is 12 kg, and another laptop that is of 3 kg, and they have different values. So a single item, so you either take it or leave it for each item. That is one possibility. Second possibility is that they are like quantities that you can take. So this is 10 kg, you can take 5 kg of this or 2 kg of this. So that means they are like loose items. So something like they can be simplest rice, dal, those sort of things. So you can take 1 kg of rice or half kg of dal. Right? There is 10 kg of rice, I can take 1 kg or I can take 2 kg. So there are 2 different types of problems. One, you either take it or leave it. So each item is take it or leave it. Second is you can take as much quantity as you want. You don't have to do it fully. Okay. Now, do you
Sir, so this sir, this $500 is amount of the whole 10 kg then for case 2?
Yes, that is the amount for the whole 10 kg. Okay, now my simple first question is, in both the cases, will you have the same solution? Will you do the same thing? If you were in case 1, what would you do? Versus if you were in case 2, what is the optimal?
But then you will take the 12 kg.
12 kg
Yes,
plus
3 kg.
plus 3 kg. How much value? $630. But if you would allow to do take it or leave it, I mean, or take as much as you can, then what is the best you could do?
10 kg whole
10 kg whole
and then 5 kg of
Plus
$540
2
one.
kg.
5 kg of 12 out of 12 kg.
Yes.
Yes. So how much you will gain? You will get $500 plus 12. So per kg, this is $45.
725.
No, per kg is
225.
45. Right? So 5 into 225.
Yes, sir.
So this is 725. So you get better in case 2. But yeah, it's not in your hand whether it is case 1 or case 2. The item will be either case 1 or case 2. Okay. And the interesting thing is that in case 1, there is no greedy approach. You have to use a DP. In case 2, you can use a greedy. Yeah. So for case 1 DP, I think Professor AM will do it next week. What happens in this case? How do you do a DP? Okay, but I'm doing greedy today. I'll just give you a brief idea. I think all of you have the approach now. Very simple. So what is the greedy approach? What is the greedy approach?
So we take the thing which is value per kg, which has the highest value per kg.
So first,
And we go by.
compute value per kg for each item. Okay, and then sort H per value by kg and take as much as you can for the first item, then take as much as you can for the second item. Okay, so yeah, so take as much as you can for the first item. If your knapsack still has some capacity left, take as much as you can for the next item. And you keep on doing that. Keep on doing that. If still some capacity, take next as much as you can for the third item, right? And keep on doing it until knapsack is full. Very simple solution, right? And complexity will be, what is the complexity? Only sorting.
So order of 1.
No, it's not order of 1.
So except sorting.
Yeah, of course. Yeah, once you sort, can we say order of 1?
So it's order n after sorting,
Yeah,
right?
because there are n things. So that is why. In the worst case, you will have to take from each of the n things. So it will be order n. Okay. So yeah, but it will be order n log n if you sort. Or sort. Now, I said this problem will look similar to a problem we have solved. Which problem is it similar to?
So that coin
change problem, right? Very good. So this is very similar to coin change problem, except that problem we did not fully abstract. We took specific coins of denomination and we proved by taking all examples. But now we are abstracting this problem. Okay, so that means I need to also do a proof. I need to do a complete proof. So let's just quickly go to the proof. Okay, I'll leave the proof whenever you think now this is trivial after that. So let's just prove it. So we have a simple strategy. Nobody can come up with a second strategy. Anybody has a second approach? Yeah, it's a simple thing. Yeah, compute value per kg and sort as per that. Take as much as you can for the first item and so on. So given 1 to n items, sorted as per value by weight ratio. Suppose you call it row. So row 1 is larger than equal to row 2, larger than equal to row 1. Let the greedy solution be x1 to xi. What is xi? Xi is in 0 to 1. It's a fraction. Indicates the fraction of item xi. Yes. And knapsack capacity is capital W. So you can make an equation immediately. What is the equation you can say now? You can form an equation now. Sigma xi what will be W. So their weights for W1 to Wn and values are V1 to Vn. And if you take their weight value by weight ratio, that is rho 1 to rho n. Now what is the equation? I took xi fraction from item 1. So what is sigma xi?
Wi.
Wi is equal to W. That is the equation. Now this is my greedy solution. How to prove optimality? Greedy solution, that is you take as much as possible of item 1 and so on. Let O, to prove optimality of G. Let O, say y1 to yn, be the optimal solution. Now what can you say? If O is not same as G, then what can you say? What is the most trivial thing you can say?
Sir, then O is not optimal.
So that's okay. But you can say something more. You can say then O
So
differs from G.
Differs at least at 2 positions.
Yeah. Okay, good. But yeah, I'm saying differs from G at least at one position, I mean to begin with. G at least for some position. Yeah, you're right. It will has to differ at multiple position, but yeah, it will differ at least at one position. So take the first position I where O differs from G. What does that mean? That means Y for 1 to I minus 1, say I'll say J. J is equal to 1 to I minus 1, Xj is same as Yj. Yes, that's what I mean. They differ only at first time they differ is positional, but xi is not same as yi. What can I say? Can I say both cases are possible? Xi can be possible greater than yi and xi can be less than yi. Are both possible? Are both cases possible?
No, sir. No, sir.
No. Why not?
So because we're already taking out the maximum in our greedy solution, so we can't take more.
Because of, yes, very good. So this case not possible because greedy solution takes as much as it can. It is not possible that yi can be larger than xi. Anybody has a doubt on that? I'm ready to discuss. So that means this is not possible. This is the only possibility. Xi will be larger than yi. Okay. So that means xi is larger than yi if they are not same. Okay, fine. But in optimal solution also, you have to fill knapsack up to the capacity. Yes. So if xi is larger than yi, that means you took less weight of item I But then you would have taken more weight from other items.
Yes, sir.
Sir, can you repeat why xi cannot be less than yu?
So my optimal solution will be some y1 to yi minus 1, yj plus 1 to yi. Okay, and what I'm saying up to here they are same as x1 to xi minus 1, and I'm saying yj is smaller than yi side. Yij is smaller than xi. Okay. Yeah, let me not even talk about this right now. Let's say yi is smaller than xi. This is the first time they differ. Now let's go back to our greedy argument. This argument to prove that this is optimal. We will say that. So let's change O to O prime. So by replacing yi with xi. So that means in O, instead of yi, let me choose xi. Let me choose xi. And I show that by doing that, I get a solution that is not worse than O. Okay. So I choose xi here, suppose. Can I just choose xi without doing anything else?
We might need to decrease some weights.
Because if I choose xi, that means I have to choose an addition. That means I am putting some weight in my knapsack. Yes, and how much weight I am putting? Xi minus yi times rho I. That much weight I am putting in my knapsack.
It should be wi.
Yeah, should be wi. Yeah, rho I is the fraction. So this much weight I'm putting in the knapsack. But that means I have to reduce that much weight from the rest of the items, later items. So that means no point of reducing this from the previous items. They were anyway a higher value. So that means I will have to reduce this much weight from the later items. Okay, from I plus 1 to n. Yes. Okay. Now what you need to prove now? Argue that the value in O prime is greater than equal to that of O. That's all you have to prove. Now, do you understand how we will prove that?
So we can take the change in value from O to O prime.
So you have to find out what is the change delta in value from O prime to O. Yes.
Sir, the weight in knapsack will be wi only. I mean, the change. Why will it be xi minus yi into wi? It is the value.
No. You see, what were xi and yi? They were fractions. They were fractions of items you were taking, and they are between 0 to 1. So what we were saying, in greedy you were taking more of item I than in O. So xi was larger than yi. So if you want to change O to O prime where yi, you want to change yi to yi prime, that is same as xi. So that means you are putting some weight in your knapsack. How much weight you are putting? You are adding fraction xi minus yi. And what is the corresponding weight? You multiply by wi. Is there a doubt with that?
So when we come to O prime from rho, we are adding extra xi minus yi times weight.
Yes. And it comes at the end.
Yes, sir.
Hmm? I'm saying this much you will have to reduce from the other items, I plus 1 to n. In some way. Okay. Now we are saying whatever way we do that, the value of O prime will be larger than that of larger than equal to that of O. So for that, what we need to do, we need to find out difference in value. Difference in value from O prime to O to O prime. How much we increased. Okay. So in ith item, up to I minus 1, there was no change. In ith item, how much I gained? Xi minus yi times wi rho I. Can I say that much value I gained?
Yes, sir.
Okay. But then
Sir, rho I is weight per kg. I mean value per kg.
Yes, yes. Rho I
Okay,
was
sir.
weight per, yeah, value, sorry, value per kg, value per weight, value per kg. So this is the actual value I'm gaining, minus everywhere else I'll lose value. So suppose from k is equal to I plus 1 to n, suppose I remove some fraction pk and corresponding value was vk. Yeah, instead of that I could have also written vk, vi. Yes, I could also write vi. They're both same. Minus summation pk vk such that summation tk wk from k is equal to I plus 1 to n is equal to what? What is this?
xi minus yi times wi.
Xi minus yi times w. Okay. Now, how will I prove it? So this is fine. This value. So let's focus on this value. And I will put this in terms of wn rho to make it easy. I have also an equation in wn rho. So summation k is equal to 1 is equal to I plus 1 to n tk wk rho k. And rho I have a fixed, I know I have sorted rho, right? What can I say? This is less than equal to what?
xi minus yi w into rho I plus 1.
Okay, yeah, in two steps. First of all, I can say about rho k. Rho k is decreasing, right? When I go from I is equal to 1 to n. Yes?
Yes, sir.
So can I say that this is less than equal to, I take rho I plus 1, the largest of this outside, sigma k is equal to I plus 1 to n pk rho k, pk wk.
Yes, sir.
Yes, I can say that because all rho I plus 2 will be less than I plus 1 and so on. This is less than equal to this. Good. So this came out. Now in this I already have equation. This is same as xi minus yi times wi equal to rho I plus 1 times xi minus yi times wi. Now what can I say? Oh, good. So this is less than equal to this. So that means this is less than equal to this. So that means this quantity is equal to xi minus yi wi rho I greater than equal to, yes, this quantity is less than equal to this, the minus of this. So this is greater than equal to minus rho I plus 1 xi minus yi wi. So can I say this is greater than equal to 0?
Yes,
Yes,
Xi
sir.
minus Wi rho I minus rho I plus 1. They are sorted, so rho I is greater than equal to rho I plus 1. So this is greater than equal to 0. So that means the value I am gaining from O to O prime is always greater than equal to 0. So that means whenever I find them different, I can make the change, and yeah, I get a solution that is at least as good as the original solution. And so that's all. That's all for this greedy problem.
So can you please explain how greater than equal to xi minus yi wi is from the blue lines?
This was clear to you?
Yes, sir.
Right. Now we just took this term and we said, oh, instead of bk, I'll use wk rho k because I have an ordering of rows. So this I wrote like this. Was that clear? Was it clear?
Yes, sir. Yes.
Okay. And this from here to here was also clear.
Yes. Yes.
That means sigma pk vkh less than equal to this quantity.
Yes. Yes. Yes, sir.
Okay. Now you take this delta difference in value. This will this minus this. Now this quantity is less than equal to this quantity. That means this whole thing will be greater than equal to this minus this.
Yes. Yes.
That is what I'm writing here. And now I can take xi minus yi times wi common and say rho I minus rho I plus 1. And you know they are sorted, so rho I is greater than equal to rho I plus 1. So this is greater than equal to 0.
Yes, sir. Got it.
Okay.
Sir.
And yes.
So like we will let us define that the smallest weight that we can add to the knapsack is delta W. Then for each choice of delta W, we will always choose that which will have greatest value. Why will we choose a smaller value? And then we can prove in that sense as well that for each unit weight added, we will choose the one with greatest row if we wish to achieve maximum value.
See, that's all right. That is your intuition. How will you formally prove that? That is how you came up with this greedy choice. That is how you came up with greedy choice. Okay.
Yes.
See, yeah, I know. See, sometimes greedy problem can be like, do I need to prove even that? That is so trivial. I mean, that is so. But yeah, that is what you need to do. Even if things look very, very trivial, or this is, I cannot think even any other way. Still, you should prove. Okay. So, and proving always goes like that. Oh, let's assume there is a solution that is different from greedy and that is optimal. You show that, oh, but wherever it differs, you can come back to greedy and let this like more optimal or not worse than that. Or this is not even possible. Thinking like here you can say this is strictly greater, somewhere you can say this is not even possible. That is also fine. A solution other than greedy is not even possible. You can even show that. But yeah, like this is a safe way saying, okay, let's say there's another solution, but you show, okay, if it differs, I can make it similar to greedy, then its optimality will not change. It will remain either same or better than what I started with. That is what I have been doing in both the problems I did today.
Okay, sir.
Sure. Yeah, I understand the dilemma. Sometimes you might feel, oh, this looks very trivial. Why do I need to prove that? But yeah, you need to. Okay, now that completes the greedy part. You know, the lab will be next week. Yes. We have done some problems. I'll give you some more problems today. So you wanted some problems on HackerRank. I think Kaushik already gave you 2. I can tell you more. Of course, you can do as many as you want. And I'll try to give you some more problems where you have the problems and the proof. Because in HackerRank, wherever you'll find problems, there will not be any proofs, I think. But I can give you some more problems to practice for proofs. Okay. But generally, you will see proof arguments are very, very similar. You go for an inversion argument, or you go for an argument, oh, this is the first place, it is different, so make that, change that. So generally, arguments are like that.
Sir, I have one thing to ask.
Hmm.
So, like in those sums, you are taking out certain assumptions, like say case 1, case 2, case 3, case 4, and taking out which is the actual one.
No, you mean the approaches?
Yes, sir. I mean the approaches. Yes. So since we are already reducing that, saving time with respect to other methods, so can't we just simply write for each case and take the minimum out of the maximum out of them instead of like proving them which is correct or which is wrong?
Now, how do you know I have written down exhaustively all possible cases? How do you know that? And why would you go for a non-efficient solution? Think about the second problem, activity selection problem. One of the choice was take the activity with the minimum incompatibilities. I didn't say at that point of time what was the cost of that greedy choice. Take the activity with the minimum compatibilities. Minimum incompatibilities. What was the complexity of that problem?
N cube.
Huh? Yeah, this is very complex. This will not be as simple as the other things that were just sorting, right? So that means even when you are choosing a greedy choice, one thing that you have to ensure, so your greedy choice should be easily computable. I don't want to make a very complex thing. Oh, take an activity with the minimum incompatibilities, but then you have to find out incompatibility for each activity and then sort them, right? And other cases you were just sorting them, right? So this was not a greedy choice even from that perspective. This is not a easily computable property, right? So if you for example use this policy, I will take the minimum, so your complexity will be much larger because you are also doing this part. So you get a even higher complexity. And the second thing is, of course, how do you know that one of this is correct? Does that answer your question?
Okay, sir, understood. Yes.
Good. Good. Okay, anything else?
Sir,
Mhm.
sir, what is the definition of greedy choice?
What is the definition of a greedy choice? A choice that you think can be used to solve the problem. A simple choice, a simple property that you can use to solve the problem, that you think you can use to solve the problem, and that should be easily computable. It's very easy. Oh, I can. Now here I'm not saying, oh, it should be easily computable means it should be order 1, it should be order n. No, that will depend on your problem. Will depend on your problem. But a choice that should be very easily computable, like given and things. Oh, if I sort them as per the deadline and take the one with the earliest deadline, easily computable property. Like here, I have n things to steal, sort them as per their values. I can say that, right? That is a greedy choice. Sort them as per their value, choose the one with the highest value. Sort them as per their weights, choose the one with the lowest weight. Or I can say sort them as per their value by weight, choose the one with the largest. So even here I could have made 3 different choices, right? So they are all easily computable because these are given to me. I can compute them in very quickly. And I can think, oh, that may be a possible solution. If I do that, I'll get a solution that may or may not be optimal. That part I have to probe. Oh, do I get an optimal solution? In dynamic, you go a very different way. You say, okay, what is the optimal substructure of this problem? How do I write general subproblem definition, and how do I write in terms of smaller problems, do a max, min? Right? It's a very different thing. Greedy is very simple. Greedy is very simple. Just think of a property. So generally sorting is there. You do some sorting. Generally you do some sorting, and then you say, okay, let's do like that. Yeah, that's a very vague definition, I know, but that's all I can say in terms of examples.
Okay, sir.
Okay, anything else?
So please share these notes.
Okay, good. Yeah, I took a bit more time. No, not bit, quite a lot of time. So tomorrow we will just take a break and do a data structure tomorrow. Okay. So fine. Thanks all.
Sir, could you please upload whatever you have given in notes till now?
Of course, that's what I do right after I finish the topic. Within a few minutes, you will find it on Teams.
Okay, sir.
Sir,
Okay, thanks. Yes,
sir,
yes.
whatever you will cover from tomorrow, will that be there in the exam?
You see what we mentioned, whatever we cover till October 8th will be in exam. So tomorrow is less than October 8th. Tomorrow comes before October 8th.
Okay, sir.
Okay, thanks.